So let's talk about one of the applications in which continuous exponential decay and continuous exponential growth applies. This is something called half-life and doubling time. And half-life you've probably talked about in your chemistry class. Half-life is the length of time it takes for population to decay to half its size. And when you talk about it in chemistry, you typically talk about it in relationship to radioactive elements decaying. Doubling time is the length of time it takes for some population to grow to double its size. So these are pretty much both lengths of time that have to do with how long it takes a population to go to half its size or to double its size. So whenever you see a half-life, it's going to be a time unit. So for instance, carbon-14, if you ever heard of carbon-14 dating, it's one of the ways that scientists date like organic remains to see how old they are. They'll check the amount of carbon-14 that's remaining in the sample, and they know how much there should be, so when they test it, they can give sort of a percentage of how much of it is left, and they can use that to estimate the date or the age of it. So carbon-14 has a half-life of 5,740 years, and so what I'm going to do is walk you through a typical half-life problem. And just know that a doubling time problem would look exactly the same, except the opposite. I'll point that out when we get there. So carbon-14 has a half-life of 5,740 years. Since it's constantly decaying, you would use the continuous growth and decay formula, which is y equals ne to the kt. And remember, anytime you're using this formula, the first time you have to do is to calculate your k. Now, when you calculate your k, you're going to need a y, an n, a k, and a t. K is what you're looking for. So if you remember the population problem that we did in class last time, we had a starting population, an ending population, and an amount of time it took to get there. That allowed us to find the k, and then to work the problem the rest of the way from there. Same thing's going to happen with half-life. You have a starting amount, an ending amount, and a time it takes to get there. Except in this time, the definition of half-life gives you the starting, ending, and amount of time. So let me show you what that means. So my half-life is a time. It's 5,740 years. Now, what the half-life is that's the amount of time it takes for the initial amount, which for us in this case is n, to go to half its size. Now, if you look on the Alex, they'll replace the n with y sub 0, but it means exactly the same thing, the starting amount. So if I start with some amount, we're not told how much we start with here, so I could just say it's n. Because I've gone a half-life, I should have half that amount at the end, or 1/2 n. So now I can plug this into the continuous growth and decay formula. And solve it for my k. So the first thing I would do is divide by n. Take the ln on both sides. Kick the baby. Remember the ln of e is 1. And so my k then is going to be ln of 1/2 over 5,740. Now that's going to be a decimal. And the decimal is going to be negative. Now don't let that throw you, because our amount is shrinking. So it makes sense that this k is negative. So I would take that number, I would store it in my calculator as k. And now I'm actually ready to solve the rest of the problem. So I'm going to come back to the original information. No, sorry, I haven't given you what the rest of the problem is yet, have I? So that k dictates how quickly this carbon-14 is going to decay. So let's say I had a sample of something in which you have 1% of the carbon-14 remaining. And I want to know how old the sample is. So now I know the k for carbon-14. So I can come back to my continuous growth and decay formula, and I know that k is that constant k I calculated in the first part. This time I want to know how old it is, so I'm looking for the time, And it's going to end up at 1% of the carbon-14 that we started with. So I started with N. 1% you can get two different ways. You can think of it as dividing it by 100, so that'd be 1 out of 100, or you can multiply it by 0.01. I'm going to choose the latter. And then plug that stuff in. And you're solving for t. So this is pretty much going to be the same math we did in the first step, but this time we're solving for t instead of k. Oops, sorry. Got a little ahead of myself there. I said ln, my screen went crazy there. So ln of 0.01 divided by that constant k will give me the time. And what I get is 38,135.734. So if I wanted to round it to the next year, I could say it's 38,136 years old. Now, you may remember there was a big nuclear disaster in Japan a few years ago called the Fukushima, at the Fukushima plant, the nuclear plant. It was an earthquake, tsunami, and it caused one of the reactors to melt down and release a whole bunch of radiation. So one of the isotopes that was released into the environment, cesium-137. Now, cesium-137 has a half-life of about 30 years. So what I want you to do as a practice problem is to go through this problem, this process that I did with carbon-14. I want you to calculate the K. By the way, this K, when you're dealing with continuous growth and decay, sometimes this is called the continuous growth or decay parameter. And you'll see that language in your ALEX topics. And then once you calculate that K, I want you to calculate how long it would take to decay to 100% of its original size. So pause the video, try that problem out, and when you come back, I'll have switched to a new screen and worked the problem out for you. So here's the work to calculate your K. I want you to notice, just like the first problem, that your final amount is 1/2 N, your initial amount is N, and the time is the half-life. That's always what this is going to look like on a half-life problem. That's always going to be your first step, is calculating the K with that information. So then when you finish the problem, you should get about 398.6 years. So this is how half-life works. Now, if you're thinking about doubling time, here's what I meant by it's the exact same math except the opposite. So you know how with half-life you start with the initial amount and you end with half the amount? Well, with doubling time, you'd start with the original amount and end with double the amount, 2n rather than 1/2 n. But the rest of the math is exactly the same.